we take this problem 76 of your textbook. Now, I have seen that problem 76 onward in your textbook, a little more complexity starts. Here, we have studied translinear motion or linear motion in earlier chapters. In this chapter, we are studying rotational motion. But under certain circumstances, a body can have both linear motion and translation motion together. I will explain you the nuances of these motions point by point when it comes during this example, during solving this problem, during solution of this problem. But you have to be a little attentive. So the problem says a hollow sphere. Firstly, it's a hollow sphere. That means we know by standard table, its moment of inertia is 2 by 3 mr square. Is released from the top of an inclined plane of inclination theta. That is the only system. See, about the system, that is the only description. Now, that means this is the inclined plane, let us say, which makes an inclination theta, and a hollow sphere is released from the top of it. Then it asks, what should be the minimum coefficient of friction to prevent sliding? Now, let me explain you. Please allow me 2 minutes time that why there can be a sliding. This body, this sphere, apparently it appears, I'll make some rough drawing here. Apparently it appears it will start rolling and it will roll down. It will roll down the inclination. But note that if there is no sufficient friction, suppose this plane is completely frictionless, then what happens? It will slide down, like our kinematics examples in earlier chapters. It can also happen that it slides down as well as it keeps on rolling. Many things can happen. For example, I'll give you an example. Let us say you think of a spin bowler in cricket. When a spin bowler in cricket, he has a ball here, and with his finger, etc., and I'm not a good artist, as I said, suppose this is the hand of the bowler. With this finger, he throws the ball, and when he throws the ball, let us say the ball starts rotating in this direction. He's a spin bowler. Now, when the ball touches the ground, then say this is the ball. It was rotating in this direction in air. So look at it carefully. If you drop a ball rotating in clockwise direction on the ground, you just drop the ball, then due to this rotation, ball will move backward due to this rotation. But when the spin bowler in the cricket, he throws the ball, while throwing, he imparts a high velocity V, as well as the ball spins. So what will happen? This ball, when it falls on the ground, it rotates as well as it moves in forward direction at high speed, whereas the translation motion is in opposite direction to the rotation. So the point that I wanted to make, that both translation and rotation can exist together, and sometimes they can be even in opposite direction, and sometimes they can be even in opposite direction. So while trying to solve this kind of a problem, you should be very careful to study the problem before trying to solve it. Now coming to our problem. Look, this ball, what are the forces acting on the ball? It has got a downward force mg, right? And this mg has a normal component mg cos theta. It has got another component along the slope, which is mg sin theta. Due to this normal component, it has got a reaction n, which is exactly equal to mg cos theta. And also there is a frictional force acting on this F, which is equal to mu into n, which is equal to mu mg cos theta. These are the forces on this ball. Now, of course, these forces has to balance. In fact, whether it will rotate only or it will not rotate, simply slide down, or it will rotate as well as slide down. All these things happen on whether happen on the values of its friction and other parameters. For the sake of drawing, let me do it like this. That is good. So let us first check one by one. I request you to be very attentive. Now, this ball, again, I draw this ball here, free body diagram of this ball here. This is the center, and here the frictional force works. And this is the radius r. So frictional force applies a torque on this, and that torque creates a anti-clockwise motion. So we write what is the torque applied by frictional force. Frictional force is equal to, frictional force is mu mg cos theta, that multiplied by the radius of the ball r. And also torque is equal to, torque tau is equal to, we know moment of inertia multiplied by angular acceleration created alpha. Right? So we can write that mu mg cos theta multiplied by r equal to, what is the moment of inertia of this hollow sphere? Is 2 by 3 mr square. 2 by 3 mr square multiplied by alpha. Here, m gets cancelled. By mistake, I have made capital and small mix-up, so gets cancelled. And r gets cancelled with r square, only one r remains here. So we have, on the right-hand side, if we take r alpha, so r alpha is equal to On the left hand side, it will become 3 by 2, 3 by 2 mu mg cos mu g cos theta. Mu g. So we got a relation R alpha equal to 3 by 2 mu g cos theta. This is so far as the tendency of rotation, right? Now, here, the as the ball is rotating, it is also sliding down. Its center of mass is sliding down. Let us say the linear acceleration is A along the slope, right? Say linear acceleration along the slope downward is equal to A. Then we just use the free body diagram again. So it has got a linear acceleration downward. So what are the downward forces? There is a downward force of mg cos theta, mg sin theta, mg downward force of mg sin theta minus there is a opposing upward force of due to friction mu mg cos theta minus mu mg cos theta. This creates the downward acceleration A. So this is equal to ma. Here once again m and m gets cancelled. So what we are left with? This linear acceleration A is equal to g sin theta minus mu g cos theta. G sin theta minus mu g cos theta. This is another relation we shall need, right? Now the condition is no slipping. It prevents slipping. Condition for no slipping. Now here, let me come back to the basic physics once again and write down a diagram. Suppose of pure rolling. I request you to go back to your textbook and study this part of pure rolling once again. Suppose any object or any spherical object, it is rolling on a body, rolling on a surface, then if it is rolling on a surface, then if it has an angular velocity omega, then its surface has a linear tangential velocity. Surface has a linear tangential velocity v equal to omega r. Now, since the surface is moving at a velocity omega r, I have taken the rotation in this direction, so the body will move in the left direction. So the center of mass will move with v. This is pure rotation. So v equal to omega r, or at the same time A equal to, if you take time derivative, then A is equal to alpha r. These are the conditions of pure rotation. Condition of pure rotation. Pure rolling. Your textbook says rolling. This is the condition of pure wave. That means whatever is the surface velocity of the object, v equal to omega r, due to angular velocity omega, is the linear velocity of the center of mass. That's all. If it is slipping forward or backward, then this equation does not hold good. So here we write, this was a part of your theory discussion. So I make a borderline here. So here we write, coming to the solution of the problem, the condition for no slipping, condition for no slipping is A is equal to R alpha. A equal to R alpha or V equal to R omega. Now we have got the value of A, we have got the value of R alpha. So this is the condition. We can easily find out condition of no slipping. So A is G sine theta, G sine theta minus mu G cos theta is equal to R alpha we have already got is 3 by 2 mu G cos theta. Now we have to find out the value of mu, so we take the parts or the terms containing mu on one side. So 3 by 2 mu G cos theta plus mu G cos theta is equal to G sine theta. From here we get 3 by 2 plus 1, that means 5 by 2. 5 by 2 mu G cos theta, mu G cos theta is equal to G sine theta. You can cancel G. You can cancel G on both sides. From here you get mu is equal to 2 by 5. Mu is equal to 2 by 5 tan theta. So this is the condition for no slipping. Condition for no value, this is the minimum value of mu. This is the minimum value of mu. Right? From here you can, I bring to your notice one thing. You know, if theta increases, tan theta increases. So to establish this equivalence, mu has to increase. That means if this inclination of the plane, if the inclination becomes more and more towards vertical, then friction has to be more, which really matches with our concept that if the plane becomes more vertical, inclines more towards vertical, then friction needs to be more because there will be a higher tendency of slipping down. On the other hand, if the inclination is very low, if theta is low, then the tendency of slipping down is less. So far, so good. There is a second part of the question. Find the kinetic energy of the ball as it moves down a length L. The friction coefficient is half the value calculated in part A. That means friction coefficient is half of the minimum value. The friction coefficient is half of the minimum value, then what will happen? Then the ball will start slipping and at the same time it will roll. Here we have to consider two motions. And what they have asked us to find out that if the ball comes down here, the ball comes down here when it's by a length of capital L, by a length of capital L, with the friction, half of this friction we have found. At that time, what is the kinetic energy? Calculate the kinetic energy. Now, it is clear that there will be two types of motion simultaneously. Of course, one thing is, I should say, very comfortable, that whenever a body has both translinear as well as rotational motion, these two motions are independent. These two motions are independent. So you can calculate these two motions separately and then just sum up the effect. It always works. So if it is slipping, that means it has got a translational motion. Find out the kinetic energy when it has dropped down by a distance L. Also find out the kinetic energy when it has dropped down the distance L. And add these two kinetic energies, you will have the answer. So we shall do that now. We shall do that now. They have said new value of mu now is equal to mu minimum by 2. That means it is now tan theta by 5. This is one thing we have got. Let us write down the equation of translatory motion. You know, this equation of translatory motion that we have wrote down earlier, that means downward force, upward frictional force is equal to mass into acceleration. So for the translational motion, I write in short trans dot motion. So for translational motion now, downward force was mg sine theta, mg sine theta, minus upward force is now mu mg cos theta, mg cos. Earlier also it was mu mg cos theta, but now we know the value of mu is equal to ma. You remove m, all m's now, that will make it simpler. So on the right hand side we have only a. So we find a is equal to g sine theta, minus, it is mu g cos theta. Now we know the value of mu. Mu is tan theta by 5 multiplied by g cos theta is equal to g sine theta minus g by 5. Now it is tan theta multiplied by cos theta. I am left with sin theta only, minus g by 5 sin theta. Now g sin theta minus g by 5 sin theta is 4 by 5 g sin theta. 4 by 5 g sin theta. So we have found the value of a. This is a. Finally, we have a linear acceleration, so it will slip down with an acceleration a. Now, to find the kinetic energy, we need to know its velocity at this point P. We know its acceleration and we know the distance it has traveled L, so we can find the velocity V. Absolutely no problem. Say its velocity when comes down by a distance L is equal to V. Say this is the velocity. Then we can write V square is equal to, it has started from 0. So V square equal to 0 plus 2AL. So this is 2AL. Now let us put the value of A. A is 4 by 5 G sine theta. A is 4 by 5 G sine theta that multiplied by L. This is equal to 8 by 5 GL sine theta. This is equal to 8 by 5 GL sine theta. So here we have found the value of V. When you have found the value of V, you can easily find the kinetic energy due to this velocity V. That will be the translational kinetic energy. So kinetic energy due to translational motion is equal to half mv square is equal to half m sorry, this was not v, this was actually v square. This was equal to v square. V square equal to half m, v square equal to half m, v square equal to 8 by 5 gl sine theta. 8 by 5 gl sine theta. This is equal to 8 by 10. This is equal to 8 by 10 mgl sine theta. mgl sine theta. This is one part of kinetic energy that is due to translational. Now we go to find out the kinetic energy due to rotational motion. The method is same as we have done earlier. Earlier, how we found out rotational acceleration? We measured the value of torque. Then we put the equation torque equal to I alpha, etc., etc. So we go by the same way, right? For rotational motion, one point here, you may ask, sir, we have got V. So rotational speed is equal to rotational speed. So V equal to omega R. I can find out omega. No, I cannot go by that because, as I said, that is the condition of pure rolling. Now it is not pure rolling. So I have to find out the rolling effect separately, completely separately. So now the torque, we have calculated torque earlier. We just repeat the same exercise once again with the known value of mu. Torque is equal to mu mg cos theta into the radius r. Torque equal to mu mg cos theta equal to r. Also, torque is equal to I alpha. I for the hollow sphere is 2 by 3 mr square alpha. So from here we can find out alpha. We do not need to write here. So from here, that means mu mg cos theta r is equal to by 3 mr square alpha. Let me write this. So 2 by 3 mr square alpha is equal to mu m g r cos theta. From here, we get the value of alpha. We can find out. So alpha is equal to 3 by 2. I cancel m on both sides first. Alpha is equal to 3 by 2 is 3 by 2r square, that multiplied by mu g r cos theta. Mu g r cos theta. This r and r square gets cancelled, only one r remains here. So this is equal to 3 by 2 mu g cos theta upon r. 3 by 2 mu g cos theta upon r. This one r remains here. Now we also know the value of mu. So this is equal to 3 by 2. Mu is now tan theta upon 5. So this is equal to 3 by 2 g cos theta divided by r multiplied by mu, which is tan theta by 5. This is equal to 3g by 10r, 3g by 10r multiplied by cos theta multiplied by tan theta is only sin theta. So we got the value of alpha. So this is alpha. Now what we have to do? Obviously, we have to find out, like we have found out earlier, what is the linear velocity of the body when it has reached the point P. Now we have to find out what is the linear velocity of the body what is the angular velocity of the body when it has reached the point P. Find out the linear velocity, we have easily used the equation v square equal to u square plus 2 alpha s, 2as. But for angular velocity, we cannot use this equation because we do not know the total rotational angle theta, which is analogous to linear displacement theta. So what do? We find out how much time the ball has taken due to its translational motion to come down to point P. That is a indirect approach, right? So let us do one thing. Let us find out. Say T is the time. Say the ball or the sphere comes down by distance L in time T. Then we can find out the value of T. So we know the equation. So we use the equation V equal to U plus AT. We use the equation V equal to U plus AT. And since U equal to 0, so T is equal to V by A. Since initial velocity U equal to 0. So time taken is V by acceleration. Now, this linear velocity, when it has reached the point P, we have found out here, look, we have found out here the value of V square. So under root of this is the linear velocity. We also found out the acceleration. We also found out the value of acceleration. So from this, we can easily find out the time t. So time t is equal to, this velocity is under root of this. Time t is under root of 8 by 10 mgl sine theta. This is the value of V. This divided by A. A is 4 by 5 g sine theta, or 4g sine theta by 5. 4g sine theta by 5. We can simplify this. We do one thing. We put the whole thing under the square root symbol. Then we have 8g m L. So there was no M here. This is 8. 8M was not there. It was 8GL sine theta. Right here, 8GL sine theta. Similarly, this M does not exist here. 8GL sine theta divided by 5, 8GL sine theta divided by 5 multiplied by, we have to make a squaring of this to bring it under the square root symbol. So on the numerator comes 25 and denominator we have 16g square, 16g square L g square sine square theta, 16g square sine square theta. Whole thing is under. Now what do you find? This 8 crosses with 16, we are left with 2. 5 crosses with 25, we are left with 5. This g crosses with g square, we are left with only 1g. So what we have here, on the numerator I have 5L sine 5L, and also sine theta and sine square theta cancels. I have only sine theta. So on the numerator I have 5L. 5L. On the denominator I have 2g sine theta. 2 sine theta whole under root. This is the time taken. So earlier we have found out the value of alpha here. Earlier we have found out the value of alpha here, where we have found out the value of alpha here. We have found out the time taken for the rolling down to the point P. So we can find out the value of omega at this point, or the linear velocity. So angular velocity, angular velocity omega, angular velocity omega at that point is given by the equation is omega is equal to omega 0 plus alpha t. Omega 0 is 0 because it started from rest. So this is equal to alpha we have got is 3g by 10 r sine theta, 3g by 10 r sine theta, and the time we have got 5L by 2G sine theta whole under root, right? It is 5L by 2G sine theta whole under root. We bring whole thing in a under root symbol. That will be easier to find out. So 3G becomes 9G square, 9G square. 3G becomes 9G square, sine theta, it becomes sine squared theta, sine squared theta divided by 10R becomes 100R square multiplied by, we had here 5L multiplied by 5L. Here I had a multiplication of 2G sine theta. Once again, we remove this G cancels with G square. I am left with only 1G. Right? And sine theta cancels with sine squared theta. I am left with only sine theta. 5 cancels with 100. I am left with 20. So what I am left with is numerator 9GL sine theta. On the numerator, I have 9GL sine theta. And in the denominator, I am left with 20 into 2 is 40, 40R square, only 40R square. Nothing else, whole under it. Right? So this is omega. Now that we have found out omega, what is kinetic energy? Kinetic energy is half I omega square. Right? Kinetic energy. So kinetic energy. So rotational kinetic energy. Rotational kinetic energy is equal to half I omega square. Equal to half I we have already determined, or it is already known, 2 by 3 mr square by 3 mr square, and omega we have just found out its square. So what we have here is 9GL sine theta, 9GL sine theta divided by 40 r square. This is the kinetic energy. Once again, we remove the points. 2 and 2 gets cancelled. 3 and 9, I am left with only 1, 3 here. And and this r square and r square gets cancelled, r square and r square gets cancelled. So in the numerator, I have only uh, 3mgl sine theta, and the denominator I have only 40. So in the numerator, I have only 3mgl sine theta. In the denominator, I have only 40. So this is the rotational kinetic energy. And earlier we have found out the kinetic energy of the translinear motion is this. Translinear motion kinetic energy. So total kinetic energy is the sum of these two kinetic energies. So total kinetic energy is equal to sum of these two kinetic energies. Translational is 8 by 10 mgl sine theta. It was 8 by 10 mgl sine theta plus rotational kinetic energy is 3 by 40 mgl sine theta. This is equal to, we have the LCM 40 here. 10s are 444 into 8 in 4 multiply 8 is 32 plus 3 35. Is 35 mgl sine theta. This is equal to, divide both by 5. This is equal to 7 by 8. 7 upon 8 mgl sine theta. This is the answer. Now, you have seen this, this kind of problem is little lengthy. And normally in your competitive examinations or board examinations, you don't have such lengthy problems. But this kind of a problem solution gives you a clear insight of how a rotational motion and translational motion, they work together simultaneously on a body. Okay? Now we shall go to the next.